So let's get started. How many of you guys have looked at a rainbow? Most of you guys have actually looked at a rainbow. How many of you guys actually have seen a rainbow? And by see, I mean, if I were to ask you some basic questions, what's the radius of a rainbow? Or what's the order of colors? We know it goes from like red to violet or blue. What's on the inside? Is it red on the inside or is it blue on the inside? What's on the outside? How many of you can answer that question? None. All right. What about if I were to ask you what the intensity of the rainbow is? What about if I asked you what time of day the rainbow would show up if there was rain? What about one rainbow or two rainbow? I heard someone discuss double rainbows a couple of days ago. So what's that phenomenon? Do you get one rainbow or two rainbows? What causes the second rainbow, if so? And if there is a second rainbow, what is the order of color for that? What is the intensity of that? What is the radius of that? Where would that show up? Right. What is the polarization? Is it polarized? If so, what's the direction of polarization for it? What causes it to be polarized if it isn't depolarized? What is the direction of polarization? Is it weakly polarized, it's sort of slightly polarized, or is it strongly polarized? Right. So what direction would a rainbow show up in? East, north, west, south? Which cardinal direction would it show up in? What's the thickness of it? So does anyone know the answer to any of those questions? So none of you guys actually have seen a rainbow. You guys have all looked at them, but none of you actually have seen a rainbow. So, well, today we'll go through all the details for that. And the physics behind this is quite simple, but the end result is indeed beautiful. And this basically is sort of the culmination of some of the topics we've been discussing for the past week or so. This includes the optics part, refraction, reflection, includes diffraction, dispersion, interference, all that stuff. So all that stuff comes into play into this one single natural phenomenon. It's quite beautiful. So I remember once when I was in undergrad, none of you guys have to take the normal English classes and all that stuff. So back then, when I was a freshman, I hated poetry. It was just boring. You'd read some poem by Wordsworth or some other old dead British guy, and you have to write 10 pages, 20 pages analyzing it. Some of them may be interesting. You can come up with some interesting explanations, but for the most part, they're boring. And I remember asking my, I think I made some comment on, I took some scientific approach to something, and the teacher's like, well, you're just destroying the beauty of this. You're just analyzing this with science and destroying the beauty. I was like, no, that's not true, because if I for instance, if I take a flower, right? Flower is beautiful. Most everyone agrees. But if I can tell you, okay, the flower is a certain shape because it can optimize the sunlight, or it's a certain color so it can attract bees for pollination. And if I had my imagination and go down to the molecular level and think about the photosynthesis process that goes on, it doesn't deter from the actual beauty. It only adds an extra dimension to that beauty. And that's something that I hope everyone can eventually appreciate. And once I made that comment, basically the professor never bothered me ever again. So, but yeah, so today we'll look at a rainbow in a quite a detailed way, and hopefully in a way that you guys will all remember. And I believe I assigned the problem on rainbows as an extra credit problem for the homework, for one of the homeworks. Right? You guys had a drop of water, and you guys were analyzing all the angles and everything from that. I think a few chapters ago. So did you guys do that problem, or just say, extra credit? I think I've done enough for this one. Who did the problem? All right, a few people did. Good. So you'll know basically at least the diagrams I'm talking about. So let's take a drop of water and dissect it, so to speak. So I'm looking at a drop of water here, and for simplicity purpose, I'll say the sun, the ray of sun is somewhere here, and its ray is coming about somewhere over here. Right? So the sun's ray is coming over there. So if I take the normal to this surface, it's going to be something like that to the center. Right? So this part here is some radius, and this angle here would be my angle of incidence. I'll just call I for convenience. So we know from simple law of reflection that once the sunlight hits this, part of that light is going to get reflected, and this will also be the angle of incidence again, right? So, but part of it we know will get diffracted and will go into the water. So let me take another surface here, and it says let's call this first point, point A. So it's going to get refracted, and it's going to go down here somewhere. And let's call whatever. Let's call whatever point this is point B. And at this point particularly, some of the rays going to get diffracted again and go out, and part of this ray will get reflected and come down here this way, right? So we have point B there, and again it'll hit this part here. Some of it will get diffracted and go out again, and some of this will get reflected from there. So over here, this is my angle of refraction. I'll call this R. By convention, I mean same thing, I have this coming at a certain angle, so this will be angle R, this will also be angle R, and if I were to split this part up here, over here I'll have angle R, over here I'll have angle R. And this angle, so if I were to take a normal line from here to here, this particular angle over here, we'll call that delta, and this angle over here we'll call that phi, right? And this point B, this is point C. So over here the direction of light has changed by an angle phi over there, and this follows from Snell's law, right? Basically the whole thing so far, the geometry for this follows from Snell's law. And there's also axial symmetry. So sun's rays coming here, if I take this axis in the middle, I could rotate it about that. So basically sun rays can hit from all throughout from this axis, and more or less you'll have axial symmetry along this sphere. And this angle delta over here, it's quite easy to calculate. If angle delta can be given by, I have 180 here, so 180 minus this, for this phi I have to have the 4r and 2i, so plus 2i minus 4r. And you guys can go home and check and make sure that's correct. And another thing is the angle of incidence for this, it could be anything from 0 degrees. So if I had some sphere here, if it's hitting straight here, I can say that's my angle 0, angle of incidence. And if it hits somewhere over here, that could be 90. So it can have anything from 0 to 90, which means that I, the range of I, goes from 0 to 90 degrees, anywhere in the middle. And from that, I can basically know what I will know what the value of I is. Now I'll know at what angle it hits the drop of water. And using Snell's law, I can calculate what the angle of refraction is, because I know the index of refraction for water, which is 1.336 or something like that. So I know the index of refraction for water. So once I know I, from measuring it, or basically if I know the sun's in a certain direction, I'll know what the angle of incidence is. So I'll know what angle of refraction is. So once I know R, I know I can calculate what delta is. And if I know what delta is, phi is just 180 minus delta. Right? So I'll know basically all the angles over there. And it just so happens that there's a minimum angle, call this delta minimum, for which a rainbow is possible, and that is 138 degrees. And by a simple arithmetic, I know that phi, the maximum value for phi, is going to have to be 42 degrees approximately. And this is actually quite crucial to the understanding of rainbows. Let me show. I made a list of the angles. Let me pull that up for you guys. See that? All right. So angle of incidence over here, if it's 0, refraction is 0 because it's just going straight through. So my delta is going to be 180. And then it's basically from there to 90, all these angles are possible. And you can see that basically the minimum angle over here is 138.4 for any one of them. Right? So that's the minimum angle for this. And again, there's a ratio of incident versus refracted. It's 1.336. That's the index of refraction for water. So these are the angles of refraction, incidence, and the angle delta, which I defined. All right. So now, moving on. Sorry. Let me leave this up for us. So let me take one drop of water here, one tiny drop, and I have sun rays coming in, or light coming in and hitting this. So, and as I mentioned, there's axial symmetry. So if you can see over there, I have the sun ray coming in, it refracts, hits it, comes out at some point C, so it basically goes through A to B, comes out at C. Right? So if I take the axial symmetry, if I were to rotate that axis, you'll get something the shape of a cone. So I'll get something for this water droplet. I'll get something like this, right? So it's going to be something of a cone shaped. And over here I'll have light, and over here no light is coming past that, right? So everything either gets refracted over there, reflected internally, whatever the case may be. So from this, there's going to be no light over here, right? And that's also because now this angle over here, we know that the phi max has to be 42 degrees. So this angle over here for this is it's going to be that whole thing, yeah. So this whole thing is going to be about 42 degrees. And there's going to be no light here because no light, the maximum angle allowed is 42 degrees, and this outside here, it's larger than 42 degrees for my phi, so there's no light that can come out of here. And now, if you look at the index of refraction for, as I mentioned before, there's different sort of indices for different colors of light in different frequencies. So if I take the index of refraction for red, which I have a red pen, so index of refraction for red is approximately 1.331, right? This means that my phi max is approximately 42.4 degrees, right? So if I look from here, by 42.4 degrees, I'll see my reds, and I don't see my blue anywhere. Oh, nope. Oh, here it is. And my index of refraction for blue is 1.343, which means that my maximum angle for this is approximately 40.7 degrees. Right? So over here, at about 42.4 degrees, I'll have red. If I now reduce this a little bit further, I'll have my blue. So the difference in indices of refraction means that you get a slightly different value for R, for the angle of refraction for each of those values, or each of those lights. And if you get a slightly different value of R, it means that you'll get a slightly different value for delta. If you get a slightly different value for delta, it means you have a slightly different value for the delta minimum, so the minimum possible angle. And of course, but that means that you have a slightly different angle for the phi max. Right? So the phi maxes changes for each of those different colors. And this means that if you look at if you look at this cone, so it looks like a cone. If you look at this cone of light that goes back in the direction of the sun over there, the outer surface of the cone, which is the largest possible value for delta, has to be red light. So it means that the outer one has to be the color red. Right? So I'll have red light on the outside for the largest possible angle. And for the smallest possible angle, the maximum, that's the maximum angle for blue, it's going to be about 40.7. So inside, wrong one. Inside I'll have cone line for blues, and everything in the middle I'll have the different pattern. And that breaking up, or the splitting up of light, is diffraction, as we discussed during our Pink Floyd lecture, right? So, and this is how it would essentially play out. And if I were to look at a screen, if I were to put a screen over here, and if I was to look at sort of the intensity that I would see, well, I'd see a circle, and over here inside I'd see white light. Right? The outer rim of that white light is going to be blue. Right? And then the outermost part I'll have red. And on the outside of this I'd have no light. And this really is just has to do with the geometry of a rainbow. There's not a whole lot of depth to it, other than just dispersion and stuff. So if I was to look at a bunch of raindrops, or let's say you are. So let's say this is the ground. You're standing here. Right, and sun is somewhere over here. It's coming from there, and so over here, I have a bunch of water raindrops everywhere, just spread out. Right, they're just individual droplets. And if I was to look from here, let's say at some angle over there, right? I'm looking at it somewhere over here, so I'm looking at that particular drop of light. Sun would hit it something like that, right? So I'm looking in that particular direction. Well, if I was looking in this particular direction, that particular direction, if I look at the red part, it would be something like this, right? So the sun ray goes in. I see the dispersion for the cone. That would look something like this. I have red on the outside, and then blue. It goes on to blue inside. So now an intelligent question to ask is, if I look in that direction, what do you see? Or what do I see if I'm looking in the direction? Nothing. I would see nothing. Because the cone is over here. That's not, the angle for the cone is now below my angle of vision over here. So as I mentioned, outside the cone, I have no light, so it wouldn't be completely dark, but it's going to be slightly dark. On the inside, I'd have completely bright light. So let's say I was to look at somewhere over here. Let's say somewhere, looking at this light over here. Sun goes in this way, and if I look at my cone, it would be something like that. So what would I see in that case? White light, exactly. Because in the middle, what I have is white light. Right? On the outer edges, I have the dispersion of light, but on the inside, I just have white light. So if I look in that direction, all I'm going to see is white light. Well, hopefully the next one is Goldilocks angle. So if I'm looking in this angle at some water droplet there, if I look somewhere here, and my red is basically falls along that angle, what do I see? Exactly. So it just so happens at that point, you catch the outer edge of that cone, and you'll see red light. And then also symmetry axial symmetry will contribute to it. So if you can basically turn around, or not turn around, but basically axial symmetry will contribute to it. So if you look at some other angle, you can slightly above, you can see the blue light and so on. So at this point, you guys are sort of getting the idea, hopefully, of how these rainbows form. And you have zillions and zillions of raindrops that contribute to this, not just one particular raindrop we're looking at. So if we're looking at the case where, again, here, and the sun is somewhere over here, right? Sun is over there, and the sun hits you, here's your shadow, right? So again, my drawings are horrible, so there's your shadow, and here's my line of reference. And let's say I'm looking at it somewhere over here, and I see a rainbow, right? So I see a rainbow over here, and of course here I have white light. So I'm looking at that rainbow. So this angle right here has to be 42 degrees for me to be able to see that rainbow, right? And that's dictated by the geometry of the cone. So if the sun is low in the horizon, then the higher the rainbow is going to be. If the sun is lower, then you can basically shift this around a little bit, and the higher the rainbow is going to be along the horizon. And if the sun is exactly 42 degrees above the horizon, somewhere there, then, or sorry, somewhere up here according to my diagram, then what you'll have is basically the rainbow will be on the ground and you won't be able to see it. Unless, of course, it's water or raindrops near where you're standing, then in principle you can see it, but likelihood goes down. And if I'm sure, you get plenty of sunshine over here. At some point, some of you may have washed a car or watered a lawn, something to that effect. And when the sun is high above, you're basically spraying the hose. You can see a small rainbow form over there, right? I'm sure most of you guys have looked at that rainbow form, right? So similar, basically the same thing. The sun is hitting the water droplets at some angle, and the angle you're looking at causes you to see a particular rainbow. And you can actually go home now and have a much better appreciation of how that's formed and volunteer to water the lawn or wash the cars. So I've washed many cars in my day. Also very meticulously. I had this ultrasonic gauge that I was able to look and see how much room I had to play with on the clear coat. And the towels I used to wipe my car was more expensive than ones I used to wipe myself. So, and they're just completely immaculate, the car. Quite beautiful. All right, so we've discussed the angle at which we can see to find the rainbow. We've discussed more or less where we can see the rainbow, what angle the sun has to be in the horizon and so on. Now let's look at the secondary rainbow. We do get a second rainbow. It is possible, and actually it happens every time, or it's supposed to happen every time. It's just the intensity of the second rainbow is really, really faint, so it's quite difficult to actually see it. So the way it happens is I have the sun ray coming into point A, gets refracted, reflected over here, comes over here to point C, and basically whatever came out of point C is what we looked at and say, okay, that's where the rainbow forms over there. Basically for the secondary rainbow, as I mentioned over here, right, light gets reflected, goes on to some point D over there, and then comes out, and whatever light comes out from there is what causes the second rainbow. And you can actually convince yourself that it does happen by looking at pictures and YouTube videos. I'm sure there's some idiot, Yosemite or some park, some guy was just tripping over a second rainbow, right? What's that? Yeah, I remember. Actually, I was telling my friend today that I was going to talk about a rainbow, and he sent me the link that he said you should show this in your class. I was like, I'm not sure that's very scientific. But in terms of the numbers for the second rainbow, basically the red part will be at an angle of 50.4 degrees, and the blue one is going to be at an angle of 53.5 degrees. Right? So there's more than 3 degrees of separation between these two. So the second rainbow is wider, but also it's fainter, so it's wider and fainter, so it's going to be quite difficult to see. And the location of the second rainbow is roughly 10 degrees above the first rainbow. So if you see the original primary rainbow, as they call it, look 10 degrees above. In principle, you should see a secondary rainbow over there. So if you see a primary rainbow at 42 degrees, then at 52 degrees, you should see the secondary rainbow. And the colors for the secondary rainbow are reversed, as you can see from this. This has a lower angle than that. So for the primary rainbow, you have red on the outside and then it goes to blue on the inside. For the secondary rainbow, you have red on the inside and then it goes on to blue on the outside. And that primarily has to do with the geometry at which it comes out at. And there's not a whole lot of explanation that goes into that. So now we can answer some of those questions I asked you in the beginning. Well, I asked you, I think the first one was what's on the inside, what's on the outside. I just answered that. For the primary one, red is always on the inside, blue is on the outside. For the secondary rainbow, you have blue on the outside, red on the inside. The radius for this, well, it's 42 degrees, right? That's when you can see the rainbow. The length obviously depends on how high in the sky it is, and the higher it is, the smaller the rainbow, right? And the whole arc will, if the whole arc goes down, then there's only a little bit of rainbow left. If you want to look at it this way, I have my red, blue, right? It goes on forever. So this is the horizon I'm looking at. This is some distance r. The lower it is to the ground, the smaller you can actually see it. So the less of the actual rainbow, the bow is left. Higher up in the ground, in the sky, you see it, the larger it will be. And it also depends on the location of the rain. Now, I also asked what the width of the rainbow was. Well, you may naively answer that, well, I have 42.4 degrees for the red, and as if I subtract that with the angle for the blue, I have 40.7. That's going to give me approximately 1.7 degrees. The answer is no, it's not that. It's a good approximation, but it's not. So the sun is not just a point in the sky, right? It's has a dimension of about half a degree in the sky. So you have to add that extra dimension of half a degree into your calculations. So if I add half a degree to this, plus around 0.5 degrees, that's going to give me like about 2 degrees, 2.2 degrees, more or less. So it's about 2 degrees is the width of the rainbow. Light intensity, well, clearly the inside of the bow will be a lot of white light, and the outside will have, the outermost part will have the red light. So the more inside it is, the more intense you can see the light. Time of day, well, the sun has to be a bit low for you to actually properly see the rainbow. Right? The higher it is, the more difficult it will be for you to see it. If it's basically 90 degrees above where you are, then it's going to be, it's going to be really difficult to see it, or it's not. You can't see it unless you're looking at the rainbow from a hose or waterfalls or something like that. So you need the sun to be sort of low, either so early in the morning or late in the evening. Best time to see the rainbow, and of course you also need rain to be able to see it. So you can't exactly dictate. So it's perfect time for a rainbow. It's gonna, let's go out and look. So you need actual rain, and so the direction is based on the time of the day. The second rainbow, as I said, yes, there is one. It's 10 degrees higher in the sky to the primary one, and the colors are reversed. And the radius for that is about 52 degrees, right? So radius for the second one is around 52 degrees, and the width of this is, well, let's see, it's 53.5 minus 50.4 plus around half a degree. Right, so this is going to be approximately around 3.5 degrees. So another phenomenon that comes into play, so far basically we discussed the dispersion, reflection, refraction, and all that stuff. Diffraction also comes into play here, and the raindrops in the sky, they can cause destructive and constructive interferences, and they can cause supernumerary rainbows. Right, it's a mouthful to say. So what happens is you have the rainbow in the sky, up in the horizon, and light scatters from that, and basically, if they're in phase, whatever light comes in, if they're in phase, and they will reinforce each other, and you'll have constructive interference, and you'll get basically light parts. You'll get whatever the light may be, red, blue, whatever the ray of light is. And for the parts where they're not in phase, then they interfere destructively. Right? They don't reinforce each other; they cancel each other out, and you get dark spots. So you actually, I'll show you a picture later on, you'll have basically rainbows inside this. So you have a number of them, and they're going to be really faint. You see, it's going to be really difficult to see that unless you enhance the contrast and so on. Actually, I think now's a good time to show that picture. Oh yeah, there it is. So pull this picture off Wikipedia. So you can see the rainbow here, the primary one, red on the outside, blue on the inside. But you can also see the really faint rainbows that go on. Can you guys see? Let me turn the lights down. You guys see that? You see the primary rainbow, and then below that you see a few other really not so intense rainbows. And those, you'll have a number of those, quite a few of those actually, and they're called supernumerary rainbows. It's a mouthful to say. And that's basically the primary bulb, and below that you have a number of other ones. And you also have something called white rainbow. So my friend actually was going to send me a picture, but he didn't have enough time. So when he went to, I forgot where it was, Alaska or Arctic, somewhere, the air was so, there was no actual rain, but the air was so cold, there was forming either moisture or ice in the atmosphere, and the sun hits it, you have the standard reflection, refraction, diffraction stuff, and then, but what you see is not just like the dispersion of different colors, you just see like a white bow, right? That's called the white rainbow, and that happens when there's no rain, but the air is really cold. And these rainbows don't have to be caused by the sun. If you're looking at say a water fountain somewhere, right, you have mist or spray that comes up from that, and even under moonlight, that light is enough to basically cause this whole phenomenon. It'll cause the reflection, refraction, diffraction, all that stuff, and you can see a rainbow even under moonlight. And it doesn't even have to be underwater there. If you, about maybe 3 to 4 times a month, if you look up at the moon, you'll see a halo around the moon that looks like a rainbow. So basically you have the diffraction around it, or the refraction and dispersion around it. And that's not caused because there's a lot of water in the moon or something. It's just that the atmosphere, the upper atmosphere has a lot of, it's really cold up there, so it's going to have a lot of ice crystals forming there. So it'll refract and disperse off of that, and you can see a halo around the moon about maybe 3 to 4 times a month. You can see that. So it's quite beautiful to look at. I never got a picture of it, so I can't show you that, but it's quite nice to look at. So now it should be the same principle with the sunlight, but we don't actually look at the sun to actually. I mean, no one's going to stare at the sun and hope to see a rainbow because the sun itself is way too intense. But with the moon, the light itself is not that intense, so you should be able to see the halo around it. Now, we haven't gotten to the question of polarization, so let's look at that. Now, the answer to this is shortly, yeah, they're extremely polarized. Rainbows are very, very polarized, in fact. And if I look at the geometry here, let me redraw this real quick. So if I have the same spherical water bubble or water, the sun hits this at some angle. And before that, let's say the angle of incidence here is about, I is around 60 degrees. If I is 60, angle of incidence 60, it means that according to this, if I is 60, if I do my math, I'll get the angle of refraction is about 40 degrees. And this is very close to the Brewster angle. Right? So Brewster's angle is what? About 37 degrees. So theta BR is approximately 37 degrees. So there's only about a 3-degree separation between the angle of refraction and Brewster angle. So light goes in, and part of it obviously gets reflected. At this point here, it's not polarized. But then it refracts and goes in. Over here also, it's not polarized. It hits this side at some angle. To that, it's 40 degrees and goes off like that. So from this point on, it hits it at 40 degrees. It's really close to the Brewster angle. So I'll get a polarization like that. So it's coming out of the board, this polarization. So, and these are plane waves going in, if you want to look at it. So it goes out, refracts, goes out. So basically, I'll get polarization going out. So if I look at, so it's sort of perpendicular to the board. So if I look at the rainbow, the type of polarization I'll have is something perpendicular to that. So something like that. So it's polarized along that. So rainbows are actually quite polarized. And at one point, I went to the beach with my friend back in LA, and it just had rained about an hour. Just it was raining, or rain moved towards the beach, something like that. But there was a rainbow that I saw. And I was telling my friend, "Look, there's a rainbow," and he's like, "No, there isn't." And I was like, "Come on, you call me blind? I mean, I see the rainbow right there." And I was like, "No, I don't see a rainbow." And I told him, "Take your sunglasses off." Because the sunglasses he had, they were polarized, and they're vertically polarized usually, the sunglasses. So, and when you look at something that's polarized with vertical polarizers, it's basically perpendicular to that degree of angle of polarization, so it's completely blocking out that light, so he wasn't able to see the rainbow. Took the glasses off, then he was able to see the rainbow, and I was like, "Oh yeah, you're right." So let me show you some pictures of rainbows, since they're always fun. Right. So this, actually there's no rainbow here, my bad, I don't know why I put that there. All right, so here, this is a rainbow as I was walking to my final sometime in December back in undergrad at UCLA. And you can see the rainbow, it's red on the outside. You can see the blue as it goes in. And you can see over here clearly the intensity of light over here is more so than out here, right? You can see you have white light here and not that white light there. And the same rainbow, different angles. That's what I had there. So this was a drawing by the maestro himself, who originally analyzed it. This is a drawing by Sir Isaac Newton to explain rainbows. So there's a primary rainbow, secondary rainbow, and so on. This is a similar drawing by another mathematician. Maybe you guys have heard of him, Descartes. I'm sure you guys have had some rules or laws that you guys had to work with that bear his name. So this is a picture by him. Now this is an interesting photo. There's a radio telescope observatory out in the boonies in New Mexico, and they're actually analyze black holes and so on. And over there you can clearly see someone took this picture. It's actually quite a famous picture for the rainbows. You can see the primary rainbow right here, red on the outside, blue on the inside, darkness over here, and you see the secondary rainbow, red on the inside, blue on the outside. You can see the brighter light over there. Obviously it's been adjusted, the contrast has been adjusted so you can see it better, but it's quite a famous picture. This is another interesting phenomenon. So this is basically caused by a diffraction. So it's not actual, you can see the white rainbow here, but this is more of it's called a fog bow or a glory. Glory is the middle part. So this is basically caused by light hitting water droplets, fog, and they disperse, and you can see basically the same relationship or same things, physics that happens inside rainbows. And in the middle where the light is intense, you can see an actual sort of rainbow. It's called a glory. Some people call this like sainthood. So if you have a picture like a shadow taken of you with the halo around it, they say like a saint or something. This is a rainbow over here. It's sort of faint, but you can see it. Red on the outside, blue on the inside here. This was outside my office. So this was taken last year, about the same time I was giving this rainbow lecture. So it coincided really well. But you can see the rainbow there. And this is another example of white bow. So there's no actual rain, but just sun hitting either the water molecules in the air, causing a white hue, white rainbow. So that's that. So we're basically going to have a short lecture today. Let me end by telling you guys why I got into physics and offering you a quote. So the reason I got into physics was in undergrad, in high school I hated it. I absolutely just abhorred it. I was good at it, but I had a horrible teacher. It was just, I did not enjoy it. The teacher was bad. There was no inspiration. It was horrible. I got into undergrad, and then the professor was actually quite good. It was quite inspiring, and that allowed me to see that physics is just merely beyond two or three classes I have to take to get to my engineering requirements. It explained all the other disciplines of science, and it encompasses every other part, biology, chemistry, and all that. And then I heard a quote from Galileo. Galileo once famously said that the entire universe is in a glass of wine. I mean, we may never know in what sense he actually meant that, but it is true that if you look at a glass of wine closely enough, you can indeed see the entire universe in it. Starting from the glass exterior itself, it is a distillation, a composition of the Earth's rocks, right? It's aged over time. And you can see the glass itself has the rocks and the stones and all that. If you look at the wine itself, it's if you look at the evaporation, the based on the wind and the weather, the reflections inside the glass, and if you add the imagination to, some imagination to it, you can see the atoms and the molecules within the wine. And from the glass itself, which is a composition of the Earth's rocks, you can derive the age of the universe, and from that the evolution of the stars. And so you may pose some interesting questions here, like what strange array of chemicals are in a wine? How did they come to be? I mean, there are ferments, enzymes, substrates, and the products of these are from that we can come to the greatest generalization of all, that all life is indeed fermentation, which is ferment. And no one discovered the chemistry of wine without discovering, as Louis Pasteur did, the cause of much disease. And so, nature may not know. Nature doesn't really divide up sciences into, or whatever we look at, into psychology, sociology, chemistry, biology. So we shouldn't have to either. So let's let the glass of wine give us one final pleasure. We can just drink it up and forget about all the physics. All right. So I hope to see you guys all on Monday, and start studying over the weekend.